But I'm saying something even crazier. Can you, in other words, compress a file ad infinitum by just running your algorithm on it again and again and again, right? I mean, if these programs compress data, why not compress the hell out of the thing and whittle it down to just 0 or 1? We recording? Oh, shall we start lecture over? Oh, this is on. Yeah. No, it's not. Now it is. All right, welcome to the end of week 8. So we take a file, like a big text file, and you want to go ahead and compress it. We'll see which version's better. You want to go ahead and compress a really big text file, so you run it through your Huffman coding program or your favorite zip program, and you get out of that a smaller file. And then you think, that's not good enough. I'm going to run it through my compression program again and again and again. Does that not suggest that we can whittle any essay you've ever written down to just a 0 or a 1?
Doesn't that just converge to just 1 bit?
All right, 2 bits.
It will converge to something much, much larger.
It will converge to something much larger than 1. OK, so what? So right. So hopefully you see the idiocy in this line of reasoning that you can just take an arbitrary file and losslessly whittle it down and down and down and down and down and down until just finally your essay is just a 0 or a 1. Because just intuitively, how the heck are you going to get the data back? But where is that equilibrium point? Or why, equivalently, can we not do that, do you think? I mean, at what point does this compression process just hit a brick wall and not work any further? Or why does it hit a brick wall? Yeah, Karen?
Once you're taking up as few bytes as you can to represent each piece of information, putting it through your Huffman code again, still give you out the same number of bytes for each piece of information.
Yeah, so that's essentially it. If you've already represented your data with, as we've seen, as few bits as possible, thereby throwing away effectively as much redundant information as possible, even algorithms like Huffman can't really find additional redundancies in the file to exploit. And by redundancies, I mean if there is a big file that has a lot of letter E's, well, you're going to see the bit pattern for the letter E a whole lot of times. But if you've already whittled that bit pattern down to as few bits as possible, for instance, just individual 1 bits, just conceptually, there's sort of a hard limit on how few bits you can use to represent a still finite list of possible characters. And sort of more fundamentally interesting, you get into conversations about this notion of entropy, which you might remember from physics or the like, whereby compression algorithms typically take advantage of a lack of entropy in a file. That is redundancy in a file. So once you get rid of patterns within a file, and once you exploit this redundancy, really what a Huffman file or a zip file looks like, if you looked at it with a hex editor or a bit editor where you could see 0s and 1s, it would actually look, even to a human, pretty darn random. There just wouldn't be many long contiguous sequences of bits in multiple places in that file because of how these algorithms are supposed to work. So that's the extent to which we'll sort of argue why we can't whittle something down to a 0 or a 1, but at least it should strike you as obvious that that couldn't possibly be the case with a lossless algorithm. So I wrote this really cool program after having learned about Bitwise operators on Wednesdays, and it's this new program with which you can lowercase or capitalize a letter. Now in the past, maybe in Caesar or programs like that, you guys did do this capitalization by first checking if some char is within a range between, say, capital A and a capital Z, or lowercase a and lowercase z. And then what did you do typically to make an uppercase letter lowercase, or vice versa? Just that line of code, what did it do essentially? Perfect. So we typically subtracted the ASCII value of one of the characters, added back another, exploiting this underlying ASCII representation whereby letters are just numbers. Well, it turns out that you can do this in another way, and this is perhaps a neat trick. This is perhaps an optimization. It's certainly illustrative of just one use for bitwise operators. So let me draw your attention to the following prefabbed example. So we've got on the board here the binary representations of the capital letter A, which, as you should recall, is just 65 in decimal. So I took the time to write out the 8 bits that represent the number 65 for the letter A. So that's its bit sequence for A in ASCII. Lowercase a is 97, remember? So I took some time and I figured out its bit pattern and I wrote it down. And I did the same thing for big Z and little z. Now looking just at capital A and little a's bit representation and Z and little z, do you notice anything interesting about their sequences? Yeah, so they only differ in one bit location, namely the 32-bit here. So this is the 1s, 2s, 4s, 16s, 1s, 2s, 4s, 8s, 16s, 32. It looks like both in the case of A and in the case of Z, they only differ in this location. So this is actually a neat thing you can exploit, because if we can just change this bit to a 1, the effect is to do what to a capital A? Lowercase it. And then in the opposite direction, if we can just somehow convert, let's see, this thing to a 1, similarly, can we make this guy lowercase? Or equivalently, if we have this guy, and if we can flip this bit to a 0, we can go in the other direction as well. And it turns out using these basic building blocks, can we do exactly this? So if I want to flip just one bit in a byte of bits, I mean, what can I do? Which of these operators can I employ? What allows you to turn on a bit, so to speak? So XOR can, but it also might affect other bits in an adverse way. But we could use it. But there's a more straightforward way. Sorry? So one's complement. So one's complement. True. So yeah, we could absolutely use one's complement, whose purpose in life is just to flip bits, but it's a byte-wise operator. So if I use one's complement, all of these operators operate on bytes of bits, even though they then proceed to operate on all of the bits individually, but all of the bits. So what other trick might we use? Well, we're running out of options since I'm leading you to the answer here, but we could actually use bitwise OR. And this is actually generally the operator that a computer scientist or programmer would use to flip bits on. So how can we do this? Well, if the goal here is to make capital A lowercase a, it would be nice if I could just add that value to the number, or really just flip its bit. Now, I don't care about the others, and I don't want to change the other bits, in fact, so I'm just going to pad the rest of this value with zeros. Well, now, which of these operators can I now perhaps obviously apply between A and this temporary value in order to turn on, so to speak, this light bulb, to flip this bit? Well, I can just OR those now together, because the OR operator says if either of the bits is a 1, turn it on. But otherwise, do nothing else. Right? So in this case, the effect is that this guy remains a 0. This guy becomes a 1, because either of them, or both, is a 1. This case remains a 1, 0, 0, 0. This guy's a 1, this is a 0. So OR those together too, and you still get out the 1. So the net effect of this approach is just to turn on the one bit that you've set in the mask, so to speak, that we've created here. OK, and how do we create this mask? Well, I'll refer you back to Wednesday when I used the left shift operator to shift a 1 over a certain number of places. But actually, it's a little easier. In fact, what is this number in decimal? So this is just 32. So I could just take a variable. If my variable happens to be this, so char C gets capital A. If I want to change this to lowercase, assuming I know it's in the range of big A to big Z, or little a and little z, assuming I already know it's in that range and thus I can exploit this pattern, well, I can just say that C gets the value of itself ORed with 32. Or if you prefer to think in hexadecimal, OX20 is the same in hexadecimal. So it's a neat little trick. How about the other direction? What do I want to do here? Well, if I want to go from lowercase z to big Z, I don't want to turn on this bit, but rather I want to turn it off. So the easiest way to do that is to use another mask that keeps all of the bits on except for that one. So ideally, we might want to do something like this. Leave this one alone, this one alone. Let's turn this guy off. 1, 1, 1, 1, 1. In other words, just like this whole fundamental idea of binary and being switches, transistors, and the like, if you want to turn off a bit, well, just turn off that bit in your mask, leave everything else on. And now what operator can I apply to little z using this mask to give me big Z? Yeah, so I can AND it together, the effect of which is to turn off any bit that lines up with a 0 bit in my mask, which is obviously just the one I care about. And so it's gone, and it becomes big Z. Now, we'll ask one last question. How do we create this mask? Well, I could certainly figure it out. In binary, or in decimal, what does this equal? That's actually kind of annoying, right? So let's come up with a better way of figuring out what this one is. Well, this mask is really the same thing as this mask, but with what done to it? ones complement. So let's change our story now. So suppose we start off with a lowercase a in C. I don't want to apply this operator because it's already in lowercase, but rather I want to now AND it with a value, but not this value, because this value is this mask. I want really the opposite of this mask. So with one little fix, I can do something like that. Or let's actually generalize it for just a moment, just to make clear exactly what these operators are applying to. If I say char mask gets, let's say, what did we have before? 32. And now I can say char gets C ANDed with the ones complement of mask. I can just flip all those bits. So we offer this as a simple example, re-implementing a wheel that you've already implemented, but in a different way. And this idea of using masks is quite common. And in fact, for problem set 6, Huff and Puff, when you actually implement part of your own compression program, you're going to want this ability, as you may have gathered from Wednesday, to write out not bytes at a time or ints at a time, but just individual bits at a time. But unfortunately, as some of you have seen over time, there's no way of expressing individual bits using C. The smallest unit of measure that exists accessibly to you is a byte. So we actually are going to provide you with a bit of code that allows you to write individual bits at a time, but we're going to do so by using a buffer, whereby you're going to write bits to our buffer, and only once you've written 8 total bits to our buffer will we then proceed to write that whole byte out to disk. And we're going to use some of these same tricks to turn bits on or off based on what type of bit you want to write out. So if you'd like to take a look at this in action after today, there's 2 programs I whipped up called 2upper and 2lower, which implement exactly this logic. And you do have printouts thereof. But very simple programs that implement this same idea. So a couple of announcements. Problem set 6 is not due for a couple of weeks. And it's not meant, as I said in a bulletin board post last night, to therefore be twice as long as past ones. But for those of you who want to take advantage of some downtime next week, we will get it out in advance of next Friday, likely by this Monday. So we'll post that to the website if you'd like to dive into it a bit early. I was never a fan of having lecture the day before a holiday, so thus will we not have lecture the day before a holiday. No lecture on Wednesday. And for those of you going to Yale this weekend, have a good trip. So any questions about bitwise operators? No? OK, so one aside. This isn't really worth spending a lot of time on because it doesn't really fundamentally enlighten one. But this is another neat trick with bitwise operators that I actually promised a long time ago. You can swap 2 values in variables using the XOR operator without needing any temporary variables. And this is kind of, if you walk yourself through it after today, kind of a neat, mind-blowing concept whereby you can move x into y and y into x simultaneously, in a sense, using this neat operator. And it's because it operates at the bitwise level. So essentially, if you want to look at this later, not only do I have a program, swap2.c in today's printouts, that implements swap using XOR operators only, also in the form of comments on the left and right columns there, do I try to make clear exactly what bits are stored in x and y at each step in the process, so that you can later, if you're interested, walk yourself through as to why swapping does in fact work with the XOR operator. And then in this next slide, I generalized it to be foo and bar so that you can think about XOR on a higher, say, mathematical level than a bitwise level. But don't worry so much if you don't follow that. It's really meant as an arcane trick for the curious. All right, so today we take a look underneath the hood at what you've been doing all of this time when you run things like GCC and make and try to relate it to the actual CPU that's been inside that box that all of you are using on NICE or the box that you own yourself. So when you go about creating and running a program, there's many different ways of viewing this world, but we can at least describe them in the form of 5 separate processes. So there's this idea when you compile code that it gets run through a preprocessor. It then gets compiled. It then gets assembled. It then gets linked. And then only when you double click the icon or type its name at the prompt does it actually get executed. And in fact, we can dive even deeper into each of these bullet points, say in a programming languages class or a hardware class. But we today are intending to give you an overview of sorts and really give you a sense of where you can go beyond in computer science within each of these realms. So I'll make mention verbally of one of these things. This notion of preprocessing is certainly relevant to C. How many of you have ever done sharp define and created a constant in a program? All right, so that's an example of a macro, so to speak, in C. And the fact that it starts with that sharp sign implies that it's a preprocessor directive. What that means is that when you type GCC, one of its mini programs within itself looks over all of your source code and processes all of those so-called macros. So effectively, when you say sharp define foo2 to define a constant number 2, calling it foo, the compiler essentially goes through all of your source code, all of that file, and literally does a copy paste of the number 2 anywhere it sees the word foo. So that's equivalent then for you actually literally typing a 2 throughout your file. Once the result is ready to go, only then does GCC proceed to compile it in a truer sense. So what does it mean to compile code? Well, we mentioned many weeks ago that when you write a program, you write it in source code typically these days, and then you go about running it through a compiler, and that compiler spits out what's called object code. Object code just being zeros and ones that are arranged in a pattern that's only understandable by the specific type of CPU they're meant to be run on. So this story no longer plays as well verbally, but back in the day we used to be able to talk about PowerPC CPUs and Intel CPUs, and this is why you can't run Mac software on a PC or PC software on a Mac, because they understand different patterns of zeros and ones. Now, most of you with newer Macs now have x86, that is Intel CPUs as well, so the lines are somewhat blurred, even though the story still kind of works because there are separate compilers for Windows machines and for Mac machines, though for different reasons. But the process fundamentally remains the same, whether you're doing this on NICE or on your own machine, Mac, PC, Linux, or the like. So source code up there is represented in that first box. There's a lame program called Hello World that does nothing other than print Hello World, the one we keep starting with. Well, it turns out when you compile, quote unquote, a program, that spits out something, even if you don't see it yourself on disk, what's called assembly code. And assembly code is just shy of being patterns and zeros and ones that the CPU ultimately understands. But it's written in just enough symbolic syntax, that is with letters and symbols, so that a human could understand it and could actually write that, him or herself, using just a basic text editor. It's much lower to the hardware, though, in the sense that you, if you're writing assembly code, need to know something about the actual CPU. So this word register, which I think we've mentioned in the past, and if you want to actually add two values together, you don't just say x plus y. Rather, you load some value into a tiny piece of memory, a register, 32 bits of memory inside the CPU. Then you explicitly load y into another register in the CPU. Then you execute a construction called add that just knows hard-coded to add whatever's in the first register plus whatever's in the second register and put the result in yet another third register. So you have to code at that level of granularity. It's really, really close to the hardware. But you don't have to, fortunately, code in the actual zeros and ones, because even that would begin, these days certainly, to push the limits of feasibility. Now this slide's us a bit of a white lie, because on a typical machine like a NICE, the assembly code that the compiler outputs actually doesn't look like this. So for simplicity's sake, this is an example of an architecture, a CPU, a fake CPU, called the ANT architecture, which has actually was developed by Harvard and has been used in this course for many years as a pedagogical tool, because it represents an interesting representative piece of hardware, a CPU, but it simplifies things so that students in years past could focus on some of the more interesting and enlightening instructions without the distraction of the dozens of instructions that Intel CPUs currently support. So for now, though, assume that this is representative of assembly code, whereby if I ran GCC on this code, something similar in spirit to this would be outputted, and then finally GCC would compile that same assembly code into zeros and ones, object code. Well, let's dive a bit deeper. Or actually, let's take a step back before diving a bit deeper. So we're going to abstract away from what the code actually looks like now and claim that if I run GCC on a program like hello.c, which contains just that one printf statement, what really is happening again is the compilation process, out of which comes assembly code, out of which comes object code, when the compiler assembles things. And here too, we're using terms somewhat interchangeably. GCC is a huge beast of a program. Back in the day, and still in some contexts, a programmer might pre-process his code, compile his code, and then assemble his code with 3 separate commands. GCC, nicely enough, automates all of these processes to make clear what's going on. But notice that hello uses printf. Where is printf declared? In what header file? Yeah, so standardio.h, which you've just been taking on faith, is what you got to do in order to use printf this whole semester. What that suggests, if we obey conventions, is that somewhere on nice is a file called standardio.c. That is the C file that implements all of the functions that are just declared in standardio.h. And this is why you guys just have to include, sharp include, another preprocessor directive in this, incidentally. And this is why you guys just have to include that file, because that tells GCC that all of those functions exist. But later, it turns out, is GCC looking at the actual C code or the object code that corresponds to that. In other words, what the picture really looks like is this. When you run GCC, even on a trivial little application like Hello World, what's really happening in theory, in parallel, is your hello.c files getting compiled to assembly. That assembly is then getting compiled to object code. Then, though, there's this other side of the world, whereby because standardio.h is mentioned in your file, that means GCC also has to go find and compile standardio.c, thereby compiling it into assembly code, assembling it into object code, and the output of those 2 processes are 2 files. And we've rarely made mention of these .o files, which probably litter many of your directories now that we've been using make and such. But hello.o and standardio.o are the 2 files that are effectively created by that process. But now there's this final third step. When the compiler, or more properly, a linker, finally gets executed, and again, GCC does all of this for you, these 2 object code files, just big files of lots of zeros and ones, somehow get combined in an intelligent way into your executable, be it hello or a.out, whereby essentially there's bits in this file that implement printf. There's bits in this file that implement main. But main needs to call these bits. So these bits effectively get pasted into, in an intelligent way, your own bits so that the end result has everything that you actually need. And this story is actually the same. Anytime you've used CS50's library, what's happening is GCC is compiling not only your code, but our CS50.c that the staff wrote, and ultimately linking them together to create this binary. And I mentioned earlier, this is a bit of a white lie, because it would be pretty stupid for GCC every time someone in this world writes hello world to go recompile standardio.c again and again and again. So it turns out on systems, there's this notion of statically linked libraries and dynamically linked libraries. If any of you who have Windows machines have ever heard of a DLL, dynamically linked library, that's the same idea. These are functions that people at Microsoft or elsewhere wrote. They already compiled it for you. They plop that file on your system so that anytime you run or compile a program on your own box, it doesn't have to go through all of those steps. It just links in that code. So this is actually why, as an aside, if you've ever installed like a shareware program that takes it upon itself to install a DLL, one or more, in your Windows system directory, and perhaps if it was written by not a very intelligent person, installs a DLL overwriting one you already have, you can actually get different versions of various Windows files, which can actually create problems. And this is actually a wonderful way to exploit a Windows machine by effectively installing your own DLL in their operating system directory, because now their code will get called anytime various programs on the machine get executed. But now we're going down a tangent. But suffice it to say, because of this ability to link one program against another, you have not only efficiency reasons, you don't have to redo things again and again, but there are dangers, potentially, if you don't have full control or full security over your system. All right. So how did we get to this point of assembly code? Well, this thing is obviously a little calculator, but it turns out it's pretty representative of a computer. So I have no idea technically how this what is this? Who knows? Texas Instruments, we'll assume. Calculator actually works. But I can hypothesize that if it's representative of a typical, albeit limited, computer, inside of that is a bunch of memory. Right? This, after all, is how it knows how to keep displaying on the screen the answers and remember what you've typed in. So let's call the memory inside of this piece of hardware registers. And for simplicity, I'm going to assume that there are 3, at least, registers in this calculator. And I'm going to assume, just to be conventional, that each of these registers is 4 bytes. That is 32 bits. So the biggest number this calculator can support is 2 or 4 billion, depending on whether you support negative numbers. Frankly, that's probably unrealistic because these screens tend never to be very long. But we'll take it as that. If I proceed to type the number 1 on the keypad, obviously, if you've ever used a calculator, that number persists, and it displays on the screen until the thing goes off or you hit another key. So it's being stored somewhere in memory, and we're going to assume that that value is really just being stored ultimately in a register. And that's 32 bits that represent some int. If I then hit the plus key, hopefully there's some other type of memory or some kind of state that the calculator can remember so that it knows not only is a number in that register, the user also just hit this button. Which button it is has to be remembered. Now I hit the number 1 again, thereby putting that value in another, say, R2 register. And when I finally hit the equal sign, this calculator, again, if representative of a computer's job in life is to figure out what instruction was executed. It's the add instruction. The add instruction is hard-coded into the hardware in this calculator to mean go to R1, go to R2, add the 2 together, put the result in R3. So when we say that a CPU has an instruction set or knows what certain patterns of bits mean, what we're really saying is that underneath the hood, somehow or other, there are these hardwired connections that tell that computer what certain sequences of bits should induce the machine to do. In this case, take 2 registers, add them together, and put the value in a 3rd register. That's the level of granularity hardware is ultimately implemented at. Well, what else is inside the box, so to speak? Well, in a computer, now building up from a calculator, there's definitely these things called registers. And if you actually look closely at the specs for CPUs, a typical CPU will have 32 registers these days, 64 registers, usually some multiple of 2, but not terribly many. Even for today's fastest processors, there's other types of memory. As Margot mentioned, L1 cache, L2 cache, RAM, disk space. So there's this whole spectrum. But registers are pretty much as close to the brain of the computer that you can get. And that's why it's the smallest quantity as well, because the computers ultimately operate on just numbers. Well, there's this thing also called a program counter. This is just kind of a variable that keeps track of where in a program the computer is currently executing. So if object code is just a bunch of zeros and ones, something's got to keep track of where the program is in the so-called text segment in those zeros and ones. And that thing's generally known as a program counter. There's memory inside of a computer. The stuff we know is RAM. You've been loving it with malloc and the like. And it's something you have very much control over at a high level like C. There's this notion of a control unit and a data path, which collectively implement the actual logic. So when I said the calculator knows what the plus key means, that means its data path or its control unit knows what to do when I've actually hit that key. And that's sort of the true brain inside the CPU that just knows how to act based on certain values. And then you have in a typical box, a typical computer, I/O devices. Anything that supports input and output, be it a keyboard, a mouse, a monitor, anything that interfaces usually with a human being in some form. Well, what is a CPU really like? Well, this is an abstraction, and you can present this in different ways. Margot presented it as a series of cores and with a similar view. But ultimately, there's registers. A register file is a collection thereof. There's some kind of control logic that keeps track of where you are in the program. And then there's the data path, which is where the mathematics and the real implementation details are hard-coded. So if you like that kind of stuff, and better yet, you like building things, a wonderful course to take after this or 51, which might still be a prereq, is CS141, which by the course's end, you actually build essentially your own CPU. Things have changed over time. I wasn't here all that long ago, but we built things the old-fashioned way with wires and breadboards and really made a CPU using little rat's nests of wires, or at least mine typically came out like that. And I have not so fond memories of the final project, which was very gratifying, but I think I was there like 6 or more hours because it was graded on like a 3-point scale, where 3 means you did it, 2 means you kind of did it, and 1 means you showed up. And we were determined, my partner and I, to get that 3. And so because we were doing everything physically and wiring connections that mean if this is wired to this and this to this means add, and this means subtract, and so forth, our pseudocode, our design doc, was actually not very correct, even though it was like 10 pages long. And we realized this on each subsequent revision thereof during the exam. And it's a tragic thing when physically, you guys have all deleted source code from Nano and whatnot. But it's actually sickly gratifying if you know this is a buggy program, or rather a buggy computer, to be able to take your hand and rip all of the wires out. There's this sick sense of gratification, but not as the hours go on. We did get it working, though. But it's a fun class. Now more of that stuff is simulated so that they can cover more, and you can fix things more easily than we could. But it's a wonderful class nonetheless. So what can a CPU actually do? What can that data path actually implement? Well, within this architecture that at least this course is presented in years past, we're dwelling on it far less this semester, but rather using it as a teaser for other directions you can take after this course. Basic instructions in a CPU are ultimately largely mathematical. So arithmetic operations like add, subtract, multiply, increment. There's this notion of load and store instructions, whereby you can go to RAM and pull values into registers or push them back into RAM. Branch instructions, so very similar to Scratch. So weeks ago, we started dabbling in what looked like a cute little environment that implemented ifs and ands and elses and such. But that's, at the end of the day, all a CPU does too. That instruction at the middle right, BEQ, branch if equal or branch if greater than, those effectively implement if conditions in hardware. So if two things are equal, branch to this location in your program. Otherwise, go to some other location is the implication. System commands. So there's usually low-level support for things like halting, bringing a halting instruction to terminate a program, in and out, dealing with memory and disk kinds of operations for which you tend to need low-level support. There's this bitwise support as well, anding values together, noring things together, shifting bits around. But the format, notice that almost all of these instructions take, and these, to be clear, are assembly instructions, albeit for an architecture called ANT, mean that if you as a programmer actually wrote ADD followed by a couple spaces and then R1 for destination, R2 for source, and R3 for source 2, what that would mean is computer should go take source 1 plus source 2 and put the answer in DST, the destination register. So you can actually code at this low level. So why does this actually work? Well, in this architecture known as ANT, which is in spirit not all that dissimilar from x86, and the Intel boxes most of you guys now own, what these instructions ultimately look like are hard-coded numbers. So even though you, the human, or GCC, the compiler, might output ADD, what that really is represented as is, in the spirit of ASCII, just a number. So there's as many numbers as there are possible instructions. Meanwhile, the codes for the registers themselves are similarly encoded as just numbers. So a human or GCC might output R3, R1, R2 for clarity's sake. But underneath it all, when you actually assemble a program, what it outputs is a pattern of zeros and ones, which, if we view them for convenience in hexadecimal, might just look like this. So what the implication is, what the numbers in these blue boxes, if you think of them not as hex numbers, but as just sequences of bits, all a program is a whole bunch of things that are structured like that. Back to back to back to back to back. And some of those do things like branching, which means you can go from here to here to here, all the way to here, all within your program. But at the end of the day, that's what a program boils down to, even if you've implemented it in something much more accessible conceptually, like C. In fact, we can take a look now at a concrete example. So if in the top box there, we have some C code, which doesn't do anything terribly interesting, but it'll keep our assembly code simple. It initializes a variable called test1 to the arbitrarily, the number 77, the variable test2 to the number 96, and then declares a third variable, total points, which is just the sum of the two. So completely uninteresting code, but it is neat if you look now underneath the hood. Suppose we compile that with GCC, or really a compiler that outputs not x86 assembly, assembly, but ant assembly, which again is this simpler assembly language, the simpler instruction set. The kinds of stuff that gets outputted looks like this. So the first line of assembly code that might get outputted is this. LC, which happens to stand for load constant. What this means is load the constant that's currently at the address described by test1 into what? So into register 5, or rather load not the value, but load the address, as the comment there says, because the next line now, LD1, is saying to do what? So this is a bit of a distraction, but this is now saying go to the address in R1 and load its value into R14. And this one too, and I'll gloss over why this is a 1 and not a 0, this now is doing the same idea, loading what's effectively test2's value into R15. The reason this works, this is an offset. And notice that down here, the actual data in your file is saying that the number 77 is stored at this byte. Turns out the number 96 comes right after it. So for the curious, why this is a 1 means go to 1 byte later to grab the second value. So it's a convenience thing there. This add instruction says take the values in R14 and R15 and put them in the register called R3. And this last instruction here, second to last, says store the value that's in R3 back in the memory location that's referenced in R5. So even if you didn't quite follow all of that, that's fine. But notice that there are some clear low-level parallels here. This idea of loading the address of test1 into a register and thereafter referring to it as R5 is pretty much a low-level implementation of the notion of what? Pointers, right? And this is what's kind of neat about C. And what you don't get with a language like Java these days is C is really little more than sexed up assembly code with nicer syntax and with more expressiveness, or at least allows you to code at a higher level. But at the end of the day, it's really not hiding most of these low-level details. In fact, this is why you can break programs so easily, can hack programs so easily, because you are, in fact, that close to the hardware. The last instruction that's executed is halt, which just means that's it for this program. Well, now to make this a little more real, what we can actually do is this. So 2 comments. So in PS5, notice that these are some of the files we gave all you, the default versions. And notice that when you run make, and most of you have probably been taking this for granted, ever since our program started getting a little more complicated with multiple source files, you started seeing not one GCC command, but multiple ones, 2 or 3 or even more if you've written your own files. One of the purposes of make in the first place was to save you guys the hassle of having to type out ridiculously long commands, not just once, but multiple times. But what's really going on? Well, this first line is compiling what file, pretty much? Speller.c. But because of these 2 flags, this flag essentially is saying go compile a C file, and this is saying output the object code as a file called speller.o. So this line is telling the same story. Now go compile dictionary.c and store its object code in a file called dictionary.o. Now recall that speller invokes your functions that are implemented and declared in the dictionary.cnh files. So now we have 2 different chunks of object code. We have that kind of story. So what's the last step that needs to happen? The so-called linking step, where those 2 programs are merged together somehow into one binary called speller. So the third line that make automatically does for you is it links speller.o against dictionary.o, and it figures out how to merge those 2 files together for you, and then outputs this now as an executable called speller. So those 3 steps are just mimicking this process, which up until now you've probably been taking for granted. And that's perfectly reasonable because there's not that much enlightening about doing all of this yourself, which is why we've begun using a so-called build tool like make. Well, let's take a look now at that simplest of programs, hello.c. So here is hello.c from, I think, week 1. And we also just saw it excerpted on the board. If I go ahead and run gcc, or rather, let me show you this make file. So in this make file, just so that I'd remember the commands myself, I made 2 targets here. I just whipped this up quickly. So if I run make assembly, what that's going to do is execute this command. If I run make both, what that's going to do is execute this command. And frankly, I just didn't think I would remember this whole thing during lecture, and I figured nor would you if we didn't put it in a make file. So all this first command is going to do is execute GCC on hello.c, but with this new flag. And take a guess what this flag might do for us, as the target's name suggests. Yeah, it's going to compile it not all the way down to object code, but it's going to stop one step short of that and give us the assembly code. So if I run make assembly, all it did was that. But if I now do an ls, in my directory is hello.s. If I open this up, hello.s, notice that I actually have x86 assembly code that is understood by a typical Pentium processor these days. And it looks similar in spirit, though certainly not identical. But the neat thing is, it actually is pretty short. I mean, arcane to be sure, but all that there is to print hello world and printing this string up here is this amount of information. And in fact, notice it says .text here. So remember our picture of memory's ultimate layout? We said there was a text segment, which we didn't dwell on. Well, here's that text segment. It's saying here is the following sequences of bit patterns that ultimately implement this program. And for the curious, you can do this now as an at-home exercise on other files you've written. If you instead run not this, but a command like this, this will output a file called hello.list, which does output assembly code too, but it weaves your own C code in it as well. So what this allows you to do, just for the technically curious, is look at what various C code you have written, say in your largest of programs, actually maps to in assembly code. And so what this file ultimately looks like is the following. So hello.list shows us that same program, but notice now the C code is embedded. It's a little sloppy, but it shows you what chunk of C code becomes what chunk of assembly code. So with that teaser, I'll leave you with that, and we'll see you on Monday.